US Physics Olympiad year 2020 USAPHO final round. Problem B2. Mirror, mirror on the wall. Consider a square room with a side length L. The bottom wall of the room is a perfect mirror. Remember that the phase of light reflected by a mirror changes by 180 degrees. A perfect monochromatic point source with the wavelength lambda is placed a distance d above the center of the mirror, where lambda much less than d, much less than L. Question A. On the right wall, an interference pattern emerges. What is the distance y between the bottom corner and the closest bright fringe above it? Hint: you may assume lambda much less y, much less L as well. Question B. You plan on running an experiment to determine lambda in a room with the L equal 40 meters, and you know that lambda is between 550 and 750 nanometers. You will measure d and y10, the distance of the 10th fringe from the corner, with the same ruler, with the markings of 1 millimeters. At what d should you place the point source to minimize your error in your lambda measurement? Roughly, what is that minimum error? Question C. Now suppose we place a transparent hemispherical shell of thickness S and the index of refraction n over the source such that all light from the source that directly strikes the right wall passes through the shell, and all light from the source that strikes the mirror first does not pass through the shell. At what y is the fringe closest to the bottommost corner now? You may find it convenient to use x, the largest integer below x. What is the spacing between the fringes now? Ignore any reflections or diffraction from the hemispherical shell. Question D. Now suppose the hemispherical shell is removed and we instead observe the interference pattern on the top wall. To the nearest integer, what is the total number of fringes that appear on the top wall? You may assume that d much less than L. Solution for problem B2. Question A. This setup is essentially a double slit experiment, with the second slit being the image of the point source on the other side of the mirror, with the additional phase shift from the mirror. The distance between the source and the spot y on the wall is given by this square root, and the distance between the image and spot y is given by this expression. Subtracting the two distances and adding in the phase shift gives us approximately this expression, which can be simplified to left side of this expression. The distance must be a multiple of lambda for interface to occur. Then this left side must be equal n lambda, where n is integer. Substantiating n equal 1 give us y equal lambda L over 8d, which is the answer for question A. Solution for question B. From a previous question, we can write that 4 dy over L plus lambda over 2 equal n lambda. In our case, n equal 10, it means that d multiplied by y10 equal 19 over 8 lambda L. For lambda equal 650 nanometers and L equal 40 meters, we have this expression, and to minimize our error, we need to equalize D and Y10, which will give us approximately 8 millimeters for both. Now, using formula for relative error, we have this expression, and if we assume that our ruler has delta D and delta Y10 equal half millimeters, we have delta lambda over lambda equal 0.09. And assume that lambda equal 650 nanometers, we have delta lambda approximately equal 60 nanometers, and distance D must be around 8 millimeters. It was a solution for question B. Solution for question C. Now the optical distance between the source and spot Y on the wall is increased by n-1 multiplied by s. Then we need this equation. To minimize y, we make m to be this one, then y equal this expression. And because n-1 s is just an offset, the spacing between the fringes does not change. It means that spacing is still lambda L over 4D. That was solution for question C. Solution for question D. Now the distance between the source and spot X on the wall is given by the square root, and the distance between the image and the spot on the wall is this one, including phase shift lambda over 2. We do not assume that X much less than L this time. Subtracting the two distances gives us roughly this expression, or using Taylor expanding, we have roughly this expression. Now we can again use approximation, and we have this one, and from here we can count what is X. X equal this expression. For X to be physical, we require that m-1/2 less or equal to 2d over lambda. Maximum X is allowed to be L over 2, so we have this inequality. From here we can find that we have this inequality, and finally we have two conditions. From one hand, m must be greater than this expression, but less than this expression. Finally, we've got a number of fringes equal this one, and the factor 2 comes from there being two sides to the interference pattern. So that was a solution for question D, and here we made all questions solved for problem B2.